This is module 2-3 of the continuation of electromagnetic principles. In this chapter, we will see about transmission lines. Especially, we will see traveling waves on transmission lines, the solutions for that. What will happen when transmission lines are terminated in a load, and what will happen when transmission lines are terminated in another line. And also, we will look into expressions for transmission line impedance in front of a boundary, that is, in the presence of multiple reflections. Transmission lines support a transverse electromagnetic field structure between its conductors. So this is the basic assumption. For example, of such cross-section that can support TEM fields, they are wire above a conducting plane, two parallel conductors, a coaxial cable, or it could be any generic coaxial structure. The shapes need not be very regular as long as the cross-section is the same and the line is fairly large compared to the wavelength, and the cross-section is very small compared to the wavelength. It is possible to have a TEM field structure. So by a TEM field structure, we also assume that we can uniquely define a voltage between conductor 1 and 2, which is an integral of electric field along any path. So it will be path independent. Whatever path you take between 1 and 2, it should yield the same value of voltage. So there is a decoupling between electric field and magnetic field when there is a TEM field structure. That is, the current in the conductor is uniquely defined by a closed integral of magnetic field intensity around this conductor. So that will uniquely give the current. So these are some of the basic conditions. Now, first, let us concentrate on this part, trying to find the correspondence between the electric and magnetic fields with voltages and currents. So this is a transmission line structure, two parallel conductors. So this is the length. The TEM wave is propagating along the Z direction. So E and H fields are perpendicular to the direction of propagation. So let us assume the E vector to be like this, and H vector is coming out of the paper, let's say. Then this is the direction of the power flow. The medium of the transmission line is characterized by its properties: conductivity, magnetic permeability, and electric permittivity. We can have a circuit representation of this transmission line. Before that, as we said before, for pure TEM, the voltage between 1 and 2 is defined as integral of E dot dl. Line integral of electric field between the conductors at C are path independent. Similarly, the current across one conductor will be closed integral of H dot dl, and the power in this Z direction is given by E cross H ds, so which is nothing but voltage times the current. So instantaneous power flow or Poynting vector in the C direction is given by the product of voltage and current at C at time t. So these are the connections between voltage and current. Now we can define that we can take a very small section of the transmission line. Let us say it is delta Z in this direction, and represent it in terms of circuit parameters that we are more familiar with. Say, for example, we can imagine an inductance which is related to the magnetic field interaction, and we can define a capacitance more related to the electric field interaction. So C and L are values per meter. So to get the absolute value for delta Z, we multiply by delta Z. Then, because of this conductivity, there will be some leakage of currents when there is a voltage difference between these two. Some current will be flowing through due to the conductivity of the medium. So that is represented by G, the conductance G per unit length multiplied by delta C. So this structure can support TEM L, C and G. Now in practice, we have always some small resistance, however good this conductor is, even if it is copper, there is some series resistance. This series resistance is not part of TEM, in the sense that there will be voltage drop across this, so you can have a destruction of the TEM wave structure. But if R is small enough, still we can assume that TEM solution is approximately valid. G does not cause any problem for TEM structure. So the resistance times delta C, that is the series resistance component. Now we can derive Telegrapher's equation for the transmission line, which are nothing but, first we equate the voltage drop across a closed loop like this. That is obtained by this. The voltage drop across this, voltage drop across this. That should be equal to the difference in voltage between these two ports. So that is written over here. Then we can write the second equation by the currents entering and leaving this node over here. So currents entering and leaving, the difference is this much, and that should be equal to the current entering over here. So you have this negative sign, and G VZT, voltage across this, plus C dV by dt. So we got the currents also. So this is the Telegrapher's equation. Now if you look at these parameters, R, L, G and C, of that, R is a property of conductor material and conductor cross section, whereas L, G and C depends also on the type of medium that you are using, whether it is air or some other medium. Now consider a lossless transmission line. It does not have any loss, that is no attenuation, that is R equal to 0, that is amplitudes are the same all along the transmission line, and no distortion, G equal to 0, no dissipation of the current along the way of the transmission line. So under this condition, the previous equations simplifies into these two equations. Rate of change of voltage with respect to space equal minus L di by dt. Similarly, special derivative of current equal to minus C time derivative of voltage. So you can manipulate these two equations by taking the second derivative and substituting one into other, which you can do at home and see that it is true. Then you will get the wave equation, a second degree differential equation. So, and here it is 1 by LC, second derivative, special derivative of voltage, second time derivative of voltage. Now we can find a solution for this wave equation using the normal rules in differential equations. And one can see that one of the solution is of the form voltage at any point in time equal to the voltage that has happened at a time earlier at c equals 0. Say, for example, voltage at space z or length along the line and at time t equal to the voltage that would have been there at c equal to 0 at a time c by v earlier. So c by v is the time required for the wave to travel up to this point, and v is the speed of the wave. So this has the form of a forward traveling wave. So v is the speed and delta t equal to z by v. So this is one of the solutions. A forward traveling wave without any attenuation and distortion is one of the solutions for this transmission line. Now comparing with the original wave equation, we get this v squared is the velocity, and second derivative of voltage with respect to space, and second derivative of voltage with respect to time. Now comparing, we get the speed v is nothing but square root of 1 by square root of LC. So this is the expression for the speed. So the speed is related to the parameter L and C. Another possible solution for wave equation is a backward traveling wave. So you can say that the wave that you present, that is present at C, would be traveling backwards. So if it is a backward traveling wave, so this kind of represents the reflection in transmission lines that we will see later. So it is T plus Z by V. So the total solution will be the sum of the forward traveling wave and the backward traveling wave. So we denote that by the symbols plus and minus in the superscript. It is also possible to find wave equations in terms of the current wave. So we can write the wave equations in terms of the current, then do the same procedure. Then you will see that that also is sum of forward and backward current waves, and we can define a impedance at 0, which is defined as square root of L by C, and related to the forward and backward traveling waves. So here the symbol is negative when we are representing in terms of voltage and impedance. This also you can derive it, and you can see for yourself that this is true as a kind of a homework. Now let us look at transmission line boundary conditions. That is, when the transmission line is abruptly ended either by a lumped impedance, or it can be another transmission line that we will see in the next page. Suppose it is terminated in a lumped impedance, and this is the reflection point here, So we call it as R. So we call IR, VR and ZR. ZR is the impedance. So VR is the net voltage over here. So this is a sum of forward and backward reflected waves over here. And the impedance, square root of L by C, is obtained either as a ratio of voltage and forward traveling voltage and forward traveling currents at zero, or as a ratio of backward traveling voltage and backward traveling current with a minus sign. Now if you say VR by IR, so boundary condition says that VR by IR, the net current here and net voltage here should be equal to ZR. So this is given by summation of forward and backward waves divided by summation of forward and backward currents. You can manipulate this and easily find that this is nothing but from this we can say that if you try to find VR minus divided by VR plus, so this is the reflection coefficient. Reflection coefficient is what the wave that is reflected back divided by the wave that is incident. So that is the reflection coefficient for the voltage. So that we define with the symbol rho. So voltage reflection coefficient from this group of expressions you can derive as the impedance, the termination impedance minus the characteristic impedance at zero divided by the sum of those impedances. So difference divided by sum. So this is the voltage reflection coefficient. Now we can derive current reflection coefficient also. So intuitively, of course, current reflection coefficients will have a negative sign in front. So we can verify that over here. That is because IR is minus VR reflection divided by Z0, and IR positive is VR positive divided by Z0. So you get the current reflection coefficient, which is negative of the voltage reflection coefficient. Now the incident power is product of the forward moving voltage and current waves, and reflected power is product of backward moving voltage and current waves. So if you take the ratio of reflected power divided by incident power and simplify it, we will get an expression for the power reflection coefficient. Or we can obtain the power reflection coefficient as a product of voltage reflection coefficient and current reflection coefficient. So this is the expression. So here there is a square. Now consider case of transmission line boundary conditions when it is terminated in another transmission line. So this situation can happen quite often in nature. You are connecting two cables of different characteristics. So let's say that cable 1 has an impedance at 0. So any current at this junction, just left of the junction, we call it as I0, and any voltage just to the left of this junction, we call it as V0, so the medium zero. Then the current that is going into the second conductor, we call it as I1, and voltage just on the right, we call it as V subscript 1, like that. And this transmission line has an impedance Z1. So note that these two currents are not the same, because some of the energy is reflected back from this point, and these two voltages are different from these two voltages. Now, reflection coefficient. For defining the reflection coefficients, we can, if these lines are quite long, we can consider it as termination in another impedance that is equal to the characteristic impedance of this line. Now here it is assumed that this line is quite long and not influenced by what is happening over here. Then the reflection coefficient is something like we derived earlier in the previous view graph. Difference in the impedances divided by sum of the impedances, and current reflection coefficient with a negative sign in front, and the power reflection coefficient, that is power that is reflecting here. That coefficient can be obtained by this expression. So this is very similar to the previous derivation. Now what is new is that we need to find what is going into this. Of course, whatever is remaining after reflecting is going into this one. So that is called transmission coefficients with a subscript T. So voltage transmission coefficient is defined as the forward wave that is going into this medium. So we call it as V1 plus. It is not the same as V1. You have to understand that V1 is a combination of forward and backward waves. So V1 plus divided by V0, forward wave that is coming in this direction along the medium 0. So that is equal to the voltage, at this point the voltages V1 plus has to be V0 plus the forward wave and the reflective wave. That will be the net voltage over here, divided by the forward wave that is going into this medium, V0 plus. So which will be equal to 1 plus, you can manipulate this and find out that this is the reflection coefficient into this medium. So that will be nothing but, if you write out those equations, and you will see that because this is 1 and this is this reflection coefficient, V0 minus by V0 plus. So you will get it as 2Z1 divided by Z1 plus Z0. So this is what you will be getting. Similarly, for the current reflection coefficients, we can write in a similar manner. Ratio of the forward wave going into this divided by the wave falling into this. So that will be equal to the sum of the forward wave plus reflected wave divided by the wave that is going into the second medium. And again, that is written as 1 plus rho 0 I. So you will see that 2Z0 divided by Z1 plus Z0. You will get it like that. So the expressions are very similar, except that for the voltage transmission coefficient, so this is the transmission coefficient. For the voltage transmission coefficients, you have Z1 here, and for the current transmission coefficient, you have Z0 over here. Then total power transmission coefficient, this is multiplication of voltage transmission coefficient and multiplication of current transmission coefficient. While talking, I might have said that reflection coefficient, but these are not reflection coefficient, transmission coefficient. The way to identify is that you look at the subscript T. T means transmission coefficients. So this is the power transmission coefficient into this line. Now, transmission line input impedance. Often you have situations in which you are connecting a short line, or it can be a long line also, to an impedance, but they are not infinite transmission lines. So you have reflections from here, reflections back. You may have multiple reflections like that. So in that case, often it is of interest to see what is the impedance at a given point X as you are looking into the load side. Say, for example, if you are connecting two instruments together, we always talk of impedance matching. This has got relevance to that. And also, when you are connecting an equipment to the ground, there also this is applicable. So a generic transmission line has a characteristic impedance which is given by square root of R plus J omega L divided by G plus J omega C. So writing the impedance at Z equal to X as the instantaneous voltage at X divided by instantaneous current at X, Vx by Ix. So this Vx and Ix include all forward and backward waves. If we consider it like that, so you can write it out, and it will be a long algebraic expressions, and simplify it, and finally you may end up in this type of relationship. Now, of that, a special case is the one that is shown over here when X equal to 0. So this is the input impedance as seen from the source side. So you have a load and you have a line, and you are connecting this load and the line together to the source. So the source will see an impedance that is given by this expression, simplified expression. So that is the input impedance from the load side, from the source side. That is equal to the characteristic impedance times, and this is a hyperbolic function, and this is the propagation constant gamma, which is frequency dependent. So from this expression you can immediately see that they are very similar, the numerator and denominator, except that this L and C are appearing at different places. So when the characteristic impedance is same as the load impedance, suppose we use a cable that is the same characteristic impedance as the load, then you see that the numerator and denominator are the same, and it becomes 1. The input impedance is nothing but the characteristic impedance. So you get a matched impedance. So this is one of the reasons why we always connect instruments together. Often it may have 50 ohm impedance, many of the standard measuring equipment that we use in the lab. So if you use that 50 ohm cable and 50 ohm impedances, then we can match. If the load impedance is not equal to characteristic impedance, then input impedance will be varying from a very low value to high value, because this is propagation constant, so it is periodic, and that depends upon the electrical length of the line. So we will look into some special cases when ZL is not equal to ZC, this kind of effects. Input impedance of transmission line. Let us look at some special cases. For simplicity, we assume a lossless transmission line, that is R equal to 0 and G equal to 0. It means that attenuation constant alpha equal to 0. Therefore, propagation constant gamma equal to J beta, where beta is 2 pi by L. Then, from the trigonometric identity, we know that hyperbolic tan function J beta L equals J tan beta L. When the length of the line is extremely small compared to the wavelength, that is beta L far less than 1, and also beta L far less than the characteristic impedance and the load, then we find that input impedance is the load impedance always. This we can verify that by looking at the previous expressions, because beta L, when it is too small, this will be equal to 0. So it means that when the line is extremely short compared to the wavelength, input impedance will be always equal to the terminating impedance. Now let us look at some other cases. Suppose a transmission line is connected to the ground, a short, ZL equal to 0. Then in this particular case, from the previous expression, from here you can get that when ZL equal to 0, you get an expression that is equal to Z input impedance equal to ZC tan beta L. So this is what you'll be getting. Now the length L can be different electrically depending upon the frequency. So assume a case in which this is a quarter wavelength, lambda by 4. Then beta L equal to pi by 2. So substituting this into this, we see that tan pi by 2 is infinity, that is sin pi by 2 by cos pi by 2. So we get the input impedance as equal to infinity, even though it is a short circuit. It should be 0, normally we assume, but it is not. It is infinity. So the earth lead will look like an open circuit. So even though you think that you have earth, it is not really a short circuit, it's an open circuit. Now consider another case in which you are deliberately leaving it open, ZL equal to infinity. Again, from the previous expression for input impedance, for this particular case you can simplify the expression to be in this form and assume that your length is 1/4 of the wavelength. Then you will find that input impedance equal to 0. So even though it is open circuit, from the equipment side it looked like a short circuit. So this is a kind of a contradiction. So this kind of funny behavior can happen at various frequencies, and this type of behavior can happen with lengths of only 78 centimeter at 100 megahertz. So even with the higher frequencies it will be even at lesser length.